Hey guys, so as promised, here's my super awkward video for you to watch while I'm not here. Alright, so this video is really just to help you wrap up the last part of activity 7.2 in your book, where you're asked to find formulas for polynomial functions given all this criteria. Alright, and so I want to sort of start by examining some formulas of polynomials that already exist, such as the two that I've given here, polynomials f and g. All right, and so just to start, let's find the zeros of both polynomials. All right, so we know that zeros are all the places where the function equals 0, right? Our x-intercepts, where your y-coordinate is 0. So what this is going to require that we do is set the function equal to 0, right? Let it output 0. So here we go. And now, yes, it's kind of easy to see the zeros when you're in factored form like this, but we're going to go ahead and go through the motions. All right, so that's us setting the first polynomial f equal to 0. All right, so now what we would do is set each individual factor equal to 0, because if this times this times this equals 0, well, one of these had better be 0. That's the only way that can happen. So let's do it. All right, in fact, you know what? Let's go ahead and let's take the -4 as well. All right, so -4 equals 0. X plus 2 cubed could equal 0. X minus 1 could equal 0, or x minus 5 to the 4th could equal 0. So now, let's solve each of these. All right, so looking at the first little mini equation, -4 equals 0. No, it doesn't. We ignore that. It never will. Okay, now the second factor, x plus 2 cubed equals 0. Oh, well, that will be true if x is equal to -2. And the third factor, well, this will be true when x is +1, and this will be true when x is +5. So we get 3 zeros here, -2, +1, and +5. Let's do the same for polynomial g. All right. So we'll set each factor equal to 0, right? Because really, if we're looking for the zeros, right, we're going to say this whole function must be outputting 0 if we are crossing the x-axis. All right, and so then again, right, if this times this equals 0, well, one of these has to be 0. All right, so we can set each little guy equal to 0 and solve. Boy, there we go, equals 0, squeeze that in. Okay. All right, and so what value of x will make the first mini equation true? Well, x equal to 0. All righty, and for the second equation, x plus 6 will be 0 when x is -6. And for the last little mini equation, x minus 2 squared will be 0 when x is equal to 2. All right, so hopefully, right, if we look at the zeros, okay, if we look at the zeros that we obtained and we look at the formulas in general, right, like up here and up here, hopefully we start to notice a pattern about how polynomial formulas look, at least how they look in factored form, right? The first thing that we notice is that if your 0 is -2, in the formula, we see a +2. If your 0 is at +5, we see a -5, right? And if our 0 is at +1, we see x minus 1. So it looks a little backwards, right? In other words, in factored form, we always seem to be looking at x minus whatever the 0 is. And so that's what we say in this fancy expression down here. All right. So all this is saying is that, right, z1, that's just the first zero of the polynomial, right? z2, that's just the second zero, and z3 is just another zero, right? So all of these are just zeros. That's all. Looks really fancy. All right, so we see that it's always x minus whatever the zero is, and that's why it looks kind of backwards in the formula. All right, we also notice some other things, right? Each of these zeros can have an exponent, right? This zero has an exponent of 3, a multiplicity of 3. This zero has an exponent of 4, a multiplicity of 4, and technically this zero has an exponent of 1, so that's multiplicity 1. So we see that each of these zeros, right, can also have their own little multiplicities. So that's all we use m for. We just used m to mean some exponent, a multiplicity. And then there is one last piece to this, right? Because there's one more piece that we're missing here, right? There's something else that we can do to change this function, right? We can put a number in front. We can give it a leading coefficient, like this -4 here, or this +3. All right, and remember, a leading coefficient, it's just a number, right? No variables, right? So that's why we write this little a in front here, right? There could be a number sitting in front. So that's how we get this sort of general structure of a polynomial function in factored form. And now we're going to use this to our advantage when trying to build polynomial functions, okay? So if we take a look at this first example here, it says give the formula for the polynomial function with a leading coefficient of -3 and zeros at 3 and -1, and both of them have a multiplicity 3. Okay, so I have, looks like just 2 zeros. So I'm going to say, I'm pretty sure polynomial f is going to look like this. It's going to have a leading coefficient. I'm going to have x minus whatever my first zero is, and that zero is going to have some multiplicity. And then I'll have x minus whatever my second zero is, and that's going to have some multiplicity as well. And they've pretty much given us all the pieces. It's just a matter of dropping the right numbers into the right place. So let's do that. They said that the leading coefficient was -3. So they just specified our value for a, so we'll write a -3 in front here. Then they told us that we had a 0 at 3, so that will be our first 0, and a 0 at -1. That will be our second 0. All right, so let's write that. X minus the first 0, so x minus 3, and then x minus the second 0, which is -1. And then they told us that both of these have a multiplicity of 3. So they basically just told us the exponents to give each of these little factors. And now, of course, I'm not going to leave it like this because this is sloppy, right? I'm going to write it as -3 times x minus 3 cubed, x plus 1 cubed. And there we go. That's a complete formula. We've got our leading coefficient, we've got our zeros filled in, and each of those zeros has its own little multiplicity. Okay, next page. All right, in this next example, it says give a formula for any polynomial function that has a degree of 5. Okay, so now this means the degree of the entire polynomial, and zeros at x equals 2, 4, and -8. So notice the key word any. So this tells me that there's more than one possibility as opposed to example 1 where they said give the formula. All right, so, well, hey, all right, it looks like I have 3 zeros. So in general, this is what my formula is going to look like, right? We can put some number out in front. Then we'll have x minus the first 0. It will have a multiplicity. X minus the second 0, it will also have a multiplicity. And then x minus the third 0. That's going to have a multiplicity as well. So let's start filling some stuff in. All right, well, they haven't given us information about a, so we'll just leave it as a. They didn't say anything about the leading coefficient. All right, but they did give me my 3 zeros, 2, 4, and 8. All right, so negative 8 rather. All right, so I'm going to start, whoops, filling these in here. All right, well, my first 0 is 2, so in goes 2. My second 0 was 4, and my last 0 was negative 8, so minus a negative 8 will actually become a plus 8. And now all we need to do is give them each the appropriate multiplicity. And that's going to come from the fact that this has to be a degree 5 polynomial. Right now, if there's nothing in the exponent, these are circles, not zeros, right? If there's nothing in here, it's assumed to be a 1. So right now, this is a polynomial of degree 3. We need to bump it up a little bit. We need to make it degree 5. So you have a couple options, right? You could say that maybe this polynomial is degree 5 because this factor has a multiplicity of 2, and this factor has a multiplicity of 2, and this factor has a multiplicity of 1. Or maybe you want to move those around, right? You could say that this has a multiplicity of 2 and this just has a multiplicity of 1. Or, hey, you could say that this one has a multiplicity of 3 and these now each have a multiplicity of 1. So any way that you can get a degree 5 polynomial, you're fine. All right, and so I'm just going to make a choice. And notice it says any polynomial. So hey, put a leading coefficient out in front. Maybe I'll put a negative 7 just for kicks. All right, and so maybe I'll say that this is x minus 2 cubed times x minus 4 times x plus 8. This is just one option, so you do you. All right. Okay, example 3. Oop, not sure why that's coming along for the ride, but we shall get rid of you. All right. Give the formula for a polynomial of degree 3 that has a 0 at 4 with a multiplicity of 2, and a 0 at 3 with a multiplicity of 1, and a y-intercept of 12. Okay, now more information. All right, so it looks like we only have 2 zeros. Okay, so let's start building. All right, so they told us that the polynomial, all right, well, we know it's going to have a leading coefficient. They didn't say anything about that yet, so we'll put a placeholder there. But they told us we have a 0 at 4, so we're going to see x minus 4, and that 0 has a multiplicity of 2. Oh, good. In you go. Then we have another 0 at 3, so we will see x minus 3, and that 0 has a multiplicity of 1, so we don't really need to write the 1 as the exponent. That's implied. And then it has a y-intercept of 12. Why would you give us that extra information? Well, not unlike the work that we did with quadratic functions, you're given an extra point so that you can solve for a, right? I can think of lots of graphs that will have these zeros, but only one of them that's going to go through that exact point. And so that's, again, the sort of that purpose of that extra information, right? So the fact that the y-intercept is 12 tells me that when I input 0 for x, I get out 12 for y. This is also a way to say that the value of function f when x equals 0 is 12. These are all different ways for me to tell you, hey, there's another point on the graph. Okay? So let's plug in the point temporarily and use that to solve for a. Okay, so when x is 0, I output 12. So 12 equals a times 0 for x. Alrighty, and 0 for x here. And then we just do some algebra. So 12 equals a times, well, let's see, negative 4 squared is positive 16, and then 0 minus 3 is just negative 3. So we arrive here. And then when we divide both sides by negative 48, we get that a is negative 1/4. Great. And so that lets us build our final polynomial function, the right one, right, as f of x equals negative 1/4 times x minus 4 squared times x minus 3. And you can graph this on Quick Graph or Desmos and verify that it has all of these things. It's got zeros at 4 and 3 and passes through the y-axis at 12. Alrighty, last but not least. Give the formula for a polynomial of degree 4. So again, that's the degree of the polynomial, not the degree of each zero. Okay, and passes through the point 112. Ooh, yay, look, extra information. We can solve for the leading coefficient. So let's start building. It's gonna look like this. F of x equals, okay, some leading coefficient, all right, and zero's at 2, so that's going to be x minus 2, and negative 1, so we'll get x minus negative 1, so that will become plus 1, and each has a multiplicity 2. So they just told us right there. Okay, and now we know the graph passes through the point 1, 12. All right, so that means that 1, 12 is on the graph, which is the same thing as saying that when I input 1, I get out 12. So let's use that information, right? I output 12 when I input 1 for x. And now I can just solve. So 12 equals a times, all right, 1 minus 2 is negative 1, and 1 plus 1 is 2. So negative 1 squared is just 1, and 2 squared is 4. So at the end of the day, I get here 12 equals 4 times a, and when I divide both sides by 4, a must be 3. So we can write our final formula as f of x equals 3 times the quantity x minus 2 squared times x plus 1 squared. Awesome. All right, with all of this information and these techniques and strategies, you should be able to finish Activity 7-2 in your book. You will be presented with some problems that give you a graph and ask you to find a formula from there. It's the same thing. All you have to do is, instead of being given the informations in a sentence, instead of being given the information in a sentence, you're given the information from a graph, and you just have to pull all of this out on your own. It's just a different way of presenting the same information, and I have the utmost confidence in you. Good luck.